Swayam Prabha. Digital India. Educated India.
So, welcome again to the new lecture of the course Properties of Materials. So, let us just briefly recap what we have done in the past few lectures. So, let me just provide you a summary of basically overall discussion that we did. So, basically at this point what we have understood is how plastic deformation occurs in metals. So, metals have this kind of stress strain curve, it is an engineering stress strain curve. So, before they, so this is the region which is, let us say, the up to this point is the, so this is stress, this is strain, up to this point is the elastic region where sigma is equal to E into E, and this region up to fracture is the, you can say, is the plastic region, and this is the region where deformation, the plastic deformation occurs. So, we saw that up to this, so this point at which your load is maximum or engineering stress is maximum called as UTS. Okay. At this point your necking begins. So, up to this point material strain hardens, and beyond this point there is a load reduction because of after necking, because of excessive reduction in the area at the neck, and then you of course have fracture. Now, the plastic deformation as we saw, so this is the region in which you plastically deform the material. So, the question was, first of all, what is the stress that is required to cause deformation? So, plastic deformation, and how does plastic deformation happen? So, plastic deformation happens by a phenomena called as slip. Slip is nothing but motion of atoms. Slip requires slip systems, which means you have a bunch of planes and directions on which slip can occur along certain directions, which are basically in most cases the close packed directions, and the planes are planes with highest atomic density which contain these slip directions. So, based on this what we calculated was resolved shear stress, and for deformation to occur this resolved shear stress has to be larger than the critical resolved shear stress. Now, so critical resolved shear stress is a material property. So, now we saw that tau RSS theoretical is way larger than tau which is experimental value, and the reason for this was presence of dislocations in the material, because if you did not have dislocations you will have to break lot of bonds for atoms to move across each other, whereas if you have dislocations extra one bond per atom for in the vicinity of dislocation, and then with the movement of dislocation this stress is lower. So, dislocation cause lowering of stress, and this stress is called as Perels-Navarro stress, tau Pn, and this was equal to G into exponential of minus 2 pi W divided by B. So, metals generally have wider dislocations as compared to ceramics. So, that is why tau Pn is much lower than G because of due to finite W. So, if W is B or 2B or 3B is of magnitude like that, then you have substantial reduction in the stress, and the Burgess vector is also for metals it is shorter, for ceramics it is larger. So, the balance between W and B provides a tau Pn which is lower than the theoretical shear strain. This is what we saw until now. So, now what we are going to see is that, so we have seen that dislocations cause presence of dislocation lowers the to cause deformation. Presence of dislocations lowers the stress required to cause the deformation. So does it mean that, so by natural intuition it means that if you increase the dislocation density, so does it mean that if we increase the dislocation density, the material should become softer, or during deformation, since we are saying dislocation moves and it creates a step, the dislocation density should go down. None of this happens. So these are the questions, and experimentally speaking, this is also not true, this is also not true. So experimental observations are different. In experimental observations, what we see is that what experimental observations show us is that the dislocation density goes up as we deform, the material, and then the stress required to cause further deformation goes up. So dislocation density, let us say rho increases as, let us say, E increases, which is a strain, and as E increases, the tau increases. So which means what we are saying is that, on the contrary, what is happening is, as we keep as we deform, the dislocation density goes up, and as the dislocation density goes up, the stress required to cause further deformation goes up. This is contrary to what we have just now said, that stress dislocations actually lower the amount of stress that is required to deform a material. And if you make the measurements, a well annealed crystal, annealed means well heat treated crystal, so something which has been held at long temperature to thermally equilibrate and then cooled slowly, which means it has lower number of defects. Well annealed crystal will have a dislocation density of 10 to the power 10. So rho the units are per meter square, and if you have a lightly deformed crystal, this showed a dislocation density of 10 to the power 12 meter cube per meter square, and if you take heavily deformed crystal, it shows a dislocation density of 10 to the power 16 per meter square. This is contrary to what we have said, because we are saying that the dislocation leaves the crystal, causes a step as we deform, which means the dislocation should reduce in number as we keep deforming the material. So why is the dislocation density increasing as we deform the material? That is a question. And the reasons lie in, because not only we eliminate the dislocations, so during deformation while slip causes dislocation to move out of crystal, which means rho should reduce. Concurrently, dislocations are produced by operation of or activation of / activation of dislocation sources. So, there are sources in the material which produce dislocations. So, this tends to increase the dislocation. So, the net effect is, so this is number 1, this is number 2, net effect is number 2 dominates over number 1 during deformation. As a result, the rho net goes up. So, as a result, the dislocation density goes up. So, this, what are these dislocation sources now? So, dislocation sources. So, we are saying that when we cause the deformation, the slip causes dislocations to move out of crystal, which means that the dislocation density should go down. That is one effect. Let us say this is rho 1, this is rho 2. Concurrently, at the same time, when you apply stress, the so we can write here, upon application of stress, dislocations are produced by operation, some of the dislocation sources which get activated or they operate upon application of stress. This leads to increase in dislocation density. The net effect is number 2 dominates over number 1. As a result, the net dislocation density goes up. So, now the question is, what are these dislocation sources? That is what we are going to look at now. Now, one of the most important sources of dislocation is called as Frank-Reed source. It is after 2 people, Frank and Reed. So, basically Frank is F.C. Frank and Reed is W.T. Reed. So, these are 2 persons who postulated the theory of dislocation sources in 1950 in Pittsburgh in USA in a symposium. So, what this Frank-Reed source is? So, Frank-Reed sources, let us say you have the real crystals have mixed dislocations, okay. They have neither completely edge. So, we can say mixture of edge and screw dislocation. So, just like dislocation loop, we have something like this, okay. So, this is the T vector. So, depending upon the net step that is being created, you will have screw and edge components. So, this is let us say the B, okay, and this is T. So, depending upon the correlation between B and T, we will have edge and screw at various sites. Now, when these are mixed dislocations, they are present in the form of curvilinear forms. So, let us see, let us make a picture of how does it look like. So, this is let us say a crystal. So, okay, Let us draw a intermediate plane first. This intermediate plane, let us say, is this. This is a plane. On this plane we have a line. Let us say this is the line, and this line goes through so this line travels in this plane in this fashion, okay. And then we have, so this is the one plane, and then we have this another plane is this, the magenta plane, and then let us say we have another plane which is this one in the back. And this fellow, it travels on this plane in this direction. So, let us say we have this segment P, A, B and Q, and the Burgess vector points in this direction. And this is, let us say, the shear stress that is applied. Now, we can see that these are different planes, and dislocation faces different situation here than there, and if these planes are inclined, then it is going to face different shear stresses also on these planes. So, basically what we are saying is that the dislocation may run through multiple planes, multiple planes, making it to rendering it, basically making it look like curved network than a straight line, making it like a curve than a straight line. So, basically inside a material, if you make a global picture, the global picture is going to look like this. So, you have a crystal something like this. So, for the sake of clarity, let us make a crystal which is something like this. In this crystal, at certain plane, let us say we have a plane here. In this plane we have a dislocation which is, let us say, like this, because we can see that dislocation is pinned on this side and this side because it has gone through different planes. So, it has gone through different planes. As a result, these are the two ends at which it gets pinned. So, when you apply stress along this direction, let us say the Burgess vector is there, the dislocation tends to balloon itself, let us say, and this is the Burgess vector, let us say. So, macroscopically speaking, the dislocation will look something like this. These are the two ends. Initially the dislocation was this, let us say this is A and B. When you apply stress, it becomes like this. When you apply further stress, it becomes like this. When you apply higher stress, it becomes like this, and when you apply even higher stress, it turns like this. And then we know from the geometry that this is, let us say, the Burgess vector, this is B, and in this case this is the T line, but T curves itself in this fashion. So, it changes its character from positive screw to negative screw, positive edge to another negative edge depending upon the orientation of T with respect to B. So, we will, so when you have these two lines approaching each other, So, as it keeps ballooning, at some point it will adopt a behavior like this. And what is this? At this point this is B. So, let us say if this is T, this is positive T, this is negative T. So, this is T, but this is T positive, this is T negative. T positive and T negative, this is T perpendicular to B. So, this is the edge kind of dislocation. So, both of these will cancel each other. So, they will cancel and then leave, and what we will left remained with is a, when you further apply stress, this will be left with what we called as a dislocation loop. So, you started from a line, this line was pinned at these two ends because the other ends were moving into other planes which could not move. So, sort of it got pinned at A and B. When you apply stress in this direction, it allows it to balloon in further direction. Let us say this is tau. So, it adopts this is the first stage, the second stage, third stage, the fourth stage, fifth stage and the sixth stage. And as you keep ballooning it, when the negative ends, when the opposite ends of dislocation come close to each other, they cancel each other. This is like, you have a dislocation, let us say you have a crystal which is like this, in which you have one dislocation and then we have another dislocation. And when we apply here stress, this guy will move in this direction, this guy moves in this direction. When they come too close to each other, they nullify each other. So, they have nullified each other at this point, but they have also given rise to a bigger loop at this point, which is a bigger dislocation. So, as you keep doing it, when the dislocation is pinned at these two ends. So, basically what we are saying is that at A and B, dislocation is pinned, which means that is at these points it cannot leave crystal or move. So, this intermediate portion between A and B will move, and this will keep ballooning itself as you keep applying the stress, and the stress that is required to move this dislocation. So, stress, so this is called as basically Frank-Reed source. Stress required to operate a Frank-Reed source is given as tau is given as mu b by L. So, we can write this as not mu, but let us say G b by L, this is shear modulus, B is the Burgess vector and L is the length of Frank-Reed source. So, larger the length is, lesser the stress that is required to operate a source, and B is the Burgess vector. So, basically what we are saying is that if you have more pinning sites in the material, which we have because materials are polycrystalline, they contain grain boundaries, they contain impurities. So, basically what we have in materials is pinning sites, and these pinning sites could be because of grain boundaries, second phases, and movement of dislocations from one plane to another. So, basically it may be mobile in one slip plane, but it may not be mobile in other slip plane because of resolved shear stress becoming not sufficient. So, let us say if you have a situation like this where you have one plane, you have another plane and you have another plane, okay, and you have a dislocation running like this, okay. So, in this plane the tau is more than tau CRSS, but in this plane and in this plane tau is less than tau CRSS. So, basically here it becomes immobile, here it becomes immobile, but here it is mobile. But since it is a continuous array of atoms, these two then acts as, so this acts as a pinning site and this also acts as a pinning site. So, basically this is immobile, this is immobile, but in between it is mobile. So, what it does is that it then operates like a Frank-Reed source. So, essentially this is what it is going to do when you apply shear stress, when you have pinning sites like grain boundaries, second phases and crisscrossing of dislocations across various planes, and this is something that you can observe in the microscope. So, this is observable in the microscope. So, we will dwell upon this further. What we are saying is that in a material, when you deform, on one hand we said that when the slip occurs, the dislocation goes out, which means that dislocation density should have gone down, but on the other hand what we observe is that there are other mechanisms, like there are mechanisms such as Frank-Reed sources which give rise to dislocation. So, you have two competing effects. On one hand dislocation density goes out, decreases because of slip, but on the other hand dislocation density goes up because of phenomena like Frank-Reed source operation, which lead to multiplication of dislocation. So, this thing, as you keep operating it, so it will give rise to multiple rings, like, so you will have one ring, you will have next ring, you will have another ring. So, this will keep creating dislocation loops. So, this leads to basically increase in dislocation density. So, these two competing phenomena leading to decrease and increase in the dislocation density leads to increase in the dislocation density as you deform, and this is because of Frank-Reed sources creating many dislocations very quickly. And this is something we will, if possible, we will see a video in the next class, how does this happen in real materials. So, what we have done is basically we have looked at operation, we have looked at how the dislocations are created in a material through operation of these Frank-Reed sources. In the next class, what we will do is that we will study that how this understanding of dislocation annihilation and dislocation creation can be used to our advantage by to make the materials stronger. So, we will do that in the next class. Thank you.